This is chapter G on work. And our first section is a little bit of a review of friction. So let's look at static friction review. And here we're going to hold a block up against the wall. The problem was inspired by Professor Rhett Elaine on the internet, where he had this problem. I'm going to do it my own way, and remember that physics is reproducible. Different scientists will do problems a little differently, but we all get to the same conclusion if we have enough data and the analysis is correct. So here is the sketch. We have a wall and we have a block, and we're going to apply a force at an angle with respect to the horizontal theta. Now there is friction, so that if we look at our force diagram, let's first of all get our force in with the angle theta with respect to the horizontal, that's F. We have gravity. Go ahead and make this mass M, force F. And we have friction. Now, how's friction gonna go here? Well, the problem we're doing is we're going to apply enough force just to hold the mass up, so the mass wants to fall down, so the friction is going to be opposing that. If you push real hard, like trying to push the mass up, well, then the friction would be against what you're trying to do. But what we're trying to do here is keep that mass barely up there, so the friction is going to be going up in this case, and then there's a normal force pushing out. So if we look at the sum of the forces in the x direction, and we go ahead and do our usual xy, where to the right is positive, it's always good to show what your positive directions are. Then we have F cosine of theta going to the right, and we have the normal force going the other way, and since there's no motion, there's no acceleration, force is 0. Then for the sum of the forces in the y direction, well, we have three things going on here. First of all, we have the force times the sine of theta, the applied force times the sine of theta going up, but also the friction is going up, and then the weight mg is going down, and that's going to sum to 0. Now we're looking at the case where the friction is going to be static friction at its maximum, because here we just are barely having the mass against the wall. So in other words, it's about to budge and come down. So we have this condition. So there are the three equations. And I like to start with the bottom equation first. And the bottom equation here is mu s times n. Then I look for where I can find n easily. And this top one gets me n easily. So if I put this top one, n is f cosine theta. And then for the next step, usually at this point, I look for the equation I haven't used yet. And the equation I haven't used yet is this one. And that's where we can put in for the F, the friction, this equation. Now we're using all three equations. And what do I want to solve for? Well, I want to solve for the applied force. I'm going to eventually want the angle that's the best angle, so I can use as little force as possible. So if we do this, we have F sine of theta. That's basically coming from this equation, F sine of theta, and then plus mu s F cosine theta. That's this piece here. And then that's going to, subtract mg and be equal to 0. So now we're going to factor out the f to have the sine of theta plus mu s cosine of theta, and that's going to equal mg. So we're basically finished. The force as a function of theta is mg divided by sine of theta plus mu s cosine of theta. And that's the nice equation that gives me the force as a function of the angle. Notice that if we look at a case where the angle is, say, I like to look at extreme cases, say 0 degrees, then the sine of 0 is 0, and the cosine is 1, so you would get mg over mu s. Now, when the angle gets increased, then this sine starts to add some, and this decreases. And I'm going to graph this for you. I'm going to show you that this is a case where you have a nice little valley. So in this case, you're pushing the mass in, and that's tough to do, harder, because if you angle a little bit, then you're going to have a component that's going up. So we're going to see the nice graph in a second that things will get better if the angle should increase a little, somewhat. So here, what we want to do to find the best angle is you take the derivative with respect to theta and set equal to 0. But that looks messy because all this stuff with the angle is in the denominator. But if you notice, the constant in the numerator, what you can realize here is that the force will be we want a minimum. We want this force. It's basically an extremum problem in calculus where you find a maximum or a minimum. And I'm going to be interested, in this case, will be a minimum. But notice that when that minimum is achieved, the denominator is a maximum, because when you divide by a large number, you get something smaller. So what I'm going to do is do the extremum problem on the denominator. So that means d sine, this is derivative, sine theta plus mu s cosine theta. The derivative with respect to theta is equal to 0, and that's easy to do because I get the cosine minus mu s sine of theta equals 0, and that gets me mu s sine of theta equals cosine of theta. That's mu s tangent of theta equals 1. So that's going to get me the tangent of theta is 1 over mu s. Now I'm going to add a little subscript here so that angle is a specific angle, while in the top case, the angle here varies. So this is the condition for the best force. And if I put that in to the force equation, I'm going to have the minimum case. It's going to be mg over the sine of theta naught plus mu s cosine theta naught. And this is going to be equal to some force minimum, the minimum force. So what I did at this point is I made a table. I made a table of these, the condition for the minimum case. So I just simply found the arc tangents and put in for the force equation here whatever angle I found. And I got this cool result where the more friction there is, coefficient of friction, the angle here gets less and less. So if there is no friction, then what you want to do is just hold it straight up. But if there's friction, then you take advantage of that and go like this, and eventually, if there were infinite amount of friction, you would need no force at all. But if there were just a little bit, you would have that angle is going to go to 0. So if you let the mu s shoot off to infinity, you'll have 1 over a large number. You basically have tangent is going to be 0. And that angle is going to be 0 degrees to give that condition. Yeah, let's look at that for a second. If you have the tangent, if you're graphing the tangent does something like this. This is the tangent of theta. Let's say that's theta naught, and this is, theta naught. So the tangent shoots up to infinity like this when you have a 90 degrees. So if the coefficient of friction goes to 0 and that the tangent's going to shoot off to infinity, you want 90 degrees, you're going to hold it up. Friction is not going to help you. It's just, you have to just hold it straight up. Then if the friction should shoot to infinity, then you get 1 over a large number is going to be going to 0. So that's here. And that would mean that you would have an angle of 0. That case where mu s goes to infinity is like having it glued to the wall. And if it's glued to the wall, then really you don't need any force. But if you relaxed it a little bit, you would then push gently in with the angle being 0. Now I want to show you a trick where you can get this function here in terms of mu s, a trick that was taught to me by a friend, a fellow physics student. And here's the trick. How do you find the sine and the cosine if you have the tangent? What you do is you make a reference triangle like this, and you set it up so your tangent of this angle is going to be 1 over mu s. So easy way to do that is put a 1 on the opposite side and a mu s on the adjacent side. Then use the Pythagorean theorem, and the hypotenuse is 1 squared plus mu s squared, and you take a square root. And now you can real easily find the sine and the cosine. The sine of theta naught is the opposite side over the hypotenuse. And the cosine of theta naught is the adjacent side. That's the mu s over the hypotenuse. And now we put these in here, and we can eliminate the angle and have the function in terms of the mu. So if we do that, we'll have here mg over, this looks a little cumbersome. I'll just put it in there, and we'll clean it up in a second. That's the mu s. Oh, there's another mu s there. So this is going to wind up being, so I'll just go ahead and write it out so that cosine will have its own mu s over the square root here. And now what I'm going to do is multiply top and bottom by that square root to get this to look a little neater. Okay, so here, this is, remember, the force that goes with the best angle. This is the square root of 1 plus mu s squared mg, and then over, this is a 1, and this is just plus mu s squared. That's neat, because now we can see there's a further simplification. We get mg over the square root of 1 plus mu s squared. I think that's a cool way of doing it, like that. So that's a key equation. And then the other key equation would be this one here. This would be the like two key equations. So is that answer reasonable? Well, let's go ahead and check. We already looked at some extreme cases. If you take the mu(s) to go to 0, where you have no friction, then this becomes the force, the best force that you're going to look at here goes to mg, and when the mu(s) goes to 0, as he pointed out, you have 90 degrees. You're holding the thing up with the mg, so that just checks out. We're just checking to make sure that we get what we expect from analyzing it earlier. And if this goes to infinity, like you nail it to the wall or glue it to the wall, then this is going to go mg over the denominator is going to go wild, so that's going to get you to 0, and that's what we said earlier. And the angle is going to be 0 when you have 1 over infinity, the limit. You're going to have a 0 there. So it checks out nicely. So here is what I did. I made a plot, and so did the professor that I looked at. He used Python. I used a spreadsheet, and I plotted this function for all the angles, and then you get this situation with different mu's. Isn't that nice? Notice that if you look at the case where here the angle is 90, now 90 degrees, remember 90 degrees, you're holding it straight up, then you're bouncing the mg, and that's what this is here. This is mg. You have 1 kilogram, so 1 kilogram times g is almost 10, 9.8, and that's, there's the 10 line up here, so that's the 9.8, say, and they all agree at the end, if you're going to hold it straight up, that's what you get. But then notice if you are investigating the different angles, that you find there's this minimum angle, like there's one like here for this case, then it looks like it's shifting a little bit over to the left here. So in other words, as the mu gets bigger and bigger, then what you're doing here is you're going from blue down to the orange one, so you're going down. So as the mu's get bigger and bigger, you're shifting, and that's what we looked at here. When the mu gets bigger and bigger, the angle shifts downward. Very nice. Nice problem. I thank the good professor for putting that up on the internet. Nice exercise.